I'm Jessica Rosenberg. I am a professor of physics and astronomy at George Mason University and director of education for our Quantum Science and Engineering Center. So yeah, we're at George Mason University here at our Arlington campus. I focus on the education workforce development part of quantum information science and engineering. So thinking about how we educate the next generation to take part in the work that's being done in those areas.
Do you think the quantum native generation will be able to achieve things we cannot even imagine now?
We hope that's the goal, right? Is how do we get this next generation to understand this stuff, to want to work on it, to be part of sort of the next breakthroughs in quantum and in science and engineering in general.
Well, let's talk about the breakthroughs then. Do you think we are far or close from a breakthrough in quantum science?
I think it depends on which part you're talking about. We've already had many that are quantum information science related, especially in sensing. So there are different pieces of using our quantum systems to actually do new and different things. And quantum sensors are here. They're doing amazing things. Quantum computing is further off. I think there are questions about how soon we'll get there. There definitely has been acceleration in the work that's been done there, but it's not yet clear that it's imminent. At the same time, it seems to be getting closer than it was, but it's been 10 years off for a long time.
Yeah, I was actually at Yale and they showed me a quantum computer, and I knew they were still like kind of behind with the technology, but actually so simple, elementary in a way. Right now is one chip, and there is a big machine that's actually cooling one chip.
Yep.
That's very elementary chip. It's like a one cable cut in half, and electrons like jump from one part to another. So yes, I can see it's very behind. On the other hand, there are other ways to do quantum computing, the optic
Sure.
part and so on, and actually some others are going faster than other ones, right?
Yes, and I think one of the challenges is we don't know which way is going to really work in the end. We don't know whether it's going to be photonics or semiconductors or superconductors, sorry, or some other technologies, right? So I think we're still figuring out those technologies. Some of the colleagues I work with are actually focusing on some of the basic physics around quantum materials because we don't have necessarily the material that's going to solve all of the problems.
Yeah.
Each one has a challenge right now, and none of them can solve all of the problems for quantum computing at this stage.
At the same time, it's not just the material, like quantum mechanics is everywhere, right? That's why they're using also photons, but they're also using just the atoms or parts of atoms. Right. And so do you think, because you also astrophysics, so do you think this this quantum mechanics is really everywhere, and it's just a question to figure how we manage to control it and to understand it to the point that we can use it for computing?
Sure. I mean, quantum mechanics is actually the physics that governs. We talk about things in terms of classical physics or Newtonian mechanics, but really that's an approximation that works for big things. And it's really hard to solve. If you want to throw a baseball and find out where it lands, you don't want to use quantum mechanics to do that. In theory, you could, and in theory, it's actually the correct way to do it. But the simplification of Newtonian mechanics makes it much simpler to do that calculation and get an answer that's correct and predictable. But as soon as you get down to things on extremely small scales, the scales of atoms and electrons, you need quantum mechanics to explain what's going to happen, to explain that deep physics. And it's now the ability to control that in new ways that's opening up computing and sensing and some of these other technologies as well.
And do you think this quantum research in quantum mechanics and especially quantum computing will reveal a new form of math or a new form of logics that once it's revealed, everything will be much easier to understand? Because it sounds like there is something about it.
Yeah, I don't. So there's sort of different pieces of that. I think the quantum mechanics is actually fairly well defined at this point. It's the algorithms that you will use to manipulate the systems through a quantum computer, for example, right? That's going to take new ways to do that. How can we do that and actually make use of these properties in new ways to do new things? That's where the math and the computation, I think, will come together in the future in ways we haven't done before, and that we're still trying to figure out. We only have a handful of algorithms that we think will work on a quantum computer. There are probably many more that one could discover, but that's where a lot of work is being done and probably needs to be done to advance the field.
The Structures of Scientific Revolution.
Oh, okay.
It's a very interesting book because it's about the, well,
So is this Kuhn?
yes.
Yes, okay, old book. This is not a new book.
Pretty old, yes,
Yeah.
from 1968 or something.
Yes.
But it's interesting because they find a pattern there for any scientific revolution.
Yeah.
And everything that was known before, at one point after a breakthrough, a discovery in science, is actually not valid anymore.
Right.
And you start with a new paradigm, right?
Yes.
And so do you think here can happen too? And maybe the other part of the book that's interesting is saying that it's also because of an educational system that doesn't allow research and challenging assumptions, scientific assumptions that are out there. And because of that, we get stuck with a mathematical assumption, a scientific assumption for a very long time until someone decides to take a very different path and discover something very different.
And I think that is one of the challenges as you sort of break some of the basic, especially physical laws, which I think Kuhn was talking about a lot in that book, right? Is when you have to do something totally new. The discovery of quantum mechanics may be a really good example of that, right? We knew there were problems with classical mechanics. There were experiments that showed that things were not right. But getting to the point of figuring out how to construct a whole new theory that will help explain, the world and explain those problems is always a challenge, because it's hard to prepare students for what they don't know, right? You can show them what they do know. I think our education system goes way too far in this direction, right? Here's what we know. Science is really about what we don't know. And we aren't good at figuring out how to teach people that and that creativity. And it's a combination of sort of grounding in what you know, but also creativity to be able to do something new. And then, of course, there's a process of convincing people that that's correct, because I think correctly, science is conservative when you totally break down norms, right? We're not going to leap to, okay, something completely new without a lot of evidence. And that takes time, and you have to build up the support. But that's important if you're going to shift an entire system. So I think there's some balance there. Yes, we want to see those breakthroughs, but we want to make sure they're correct before you tear down everything that you've done before. So there's really that balance of pushing the next generation to be creative, to try new things, but also understanding that once you do that, if you find something new, you need to find a whole lot of evidence to support it. We've done huge numbers of experiments that have time and time again verified quantum mechanics, right? So there may be problems in there still, as there are with other parts of physics, that we're still trying to understand. As I said, I'm an astronomer. We have this thing, dark matter, which we can't explain. That's a problem. But even finding something new, finding an explanation, will need to actually take lots of tests to say, yes, this seems like a good one, right? You have to go through that process. But it's important to make those tests, have people willing to try something new, to sort of go out on a limb on some theory that maybe isn't well accepted, and run the data, run those tests, see if it works.
Yeah, it's the book is The Structure of Scientific Revolutions. And in the book, actually, it's also said that all the instruments for measuring scientific experiments are made to prove the same thing that's already proven. And so all the evidence that are found are then the same to prove something that was already proven. And that actually is a very big limitation. Of course, it's not always the case.
Right, because we do progress, but it is a challenge, right? Because that's the world you know. And so it does take those thinkers that sort of move outside of that and do something different.
And so do you think we might approach something like this also in quantum? Again, quantum mechanics, as you said, we kind of understood, or at least how it works by principle, let's say.
Yes.
But there could be something else in the quantum information that could be revealed that we don't know, we don't understand.
Sure, it's certainly possible. I think often, I mean, the way I think about it, but I'm not deeply into some of the technical aspects to know, and there may be things there that I don't know about. A lot of quantum information science is about taking this physics that we understand and trying to use it to develop technology, right? It's that translation into technology more than what is it we don't understand about the world broadly, and how do we develop things to do that? Now, that said, right, there's math, there's algorithms. Figuring out how to do that in new ways is really important, and being creative in those solutions will make a difference in how that progress happens. But I think it's a little bit different than sort of, are the fundamental physics, fundamental laws of nature, not what we think they are? That's a different kind of question, which is a little bit more, I think, what some of the structure of scientific revolutions is about in that piece. But still, with this translation, understanding how we make those breakthroughs to technology is an interesting question.
Yeah, no, I was saying that especially for the quantum computers, that again, they look very primitive in a way.
Yes.
But maybe there is, once there is a breakthrough in the knowledge, not about the chip itself, not how having multiple qubits,
right,
but actually the logics that make that qubit work in a certain way, then you don't need that kind of hardware. Maybe you need something else that we didn't even figure yet. And maybe it's not even hardware, maybe it's like quantum information again. And that would make completely different kind of engineering of computing and everything else with that. That's what I was referring to.
Yeah, no, I think that's true, right? Is figuring out what that is. Is it light? Is it, you know, a superconductor? Is it something? Is it an atom? Is it something else? And that is something we don't know yet.
A new paper that was published a week ago, something like that, within these days, and it says they are able to do the factoring problem, basically the Peter Shor algorithm, a version of Peter Shor algorithm, with 1 qubit. So.
Wow.
Until a week before, they were counting how many qubits they needed to do that, to run that algorithm, right? Now they figure they can do it with 1 qubit, but there is a catch. It takes the power of 2 stars together to run that algorithm on 1 qubit. So it's still not, of course, efficient.
Right. But no, I think it will take different ways of thinking about the problem. Absolutely, on sort of the algorithm side to make progress, because sure, we have a handful of algorithms, but maybe there are ways to do it with fewer qubits, with our noisy qubits, with these other, you know, types of qubits, and then the other problems that we want to solve as well. We're not entirely sure how to do it yet. It's like there's potential to do all sorts of things with our quantum computers, but I think not all of them do we really know what the best way to do that is yet, and it's going to take people thinking differently about the problem to get there.
Yeah, true. Once you have the computer itself, we will be also in a very different world, because once it's there, I mean, it's a 1 million more powerful than the computer we have or something?
On certain problems. And there have, I mean, right, this is probably getting to where we're going, but the reason it's become such a big deal is there's at least one algorithm that has been written that has been shown that with a standard quantum computer and a certain number of qubits, you can break encryption. That's one problem. That's not all of them that they can solve. But at the same time, quantum computers it's not obvious how it would solve other problems. I mean, people work on optimization problems in particular, things like how molecules go together, which will be important for drug discovery, how you optimize traffic patterns, all sorts of things people are looking at that we might be able to solve if we can come up with interesting ways to do it. And there people developed some algorithms for those things, but there's a long way to go to really understand how to use a quantum computer for more than one problem.
If we want to share that discovery, scientific discovery, how do we get into the schools? Because that means a completely new field of teaching and
Right, and that's where we've been trying to go is how do we start? Because we've been talking to teachers, so not only working with our graduate students, with our undergraduates who are maybe better positioned to start thinking about some of these questions, but when you talk about teachers in, say, K-12, they're maybe less ready to really think about this. And how do we help them think about it, think about why it might be important for their students, and even now, important for their students with the idea that in 10 years or more, when they're actually going out into the world deciding what their career paths are going to be, this may be very relevant to them.
yeah, it's a very good question because actually now that I think quantum research or quantum studying is only in computer science, is it?
Well, most quantum studying and research is in physics. So quantum information science is in physics, it's in math, it's in computer science, it's in many of our engineering disciplines. And actually that's been a challenge at undergraduate and graduate levels of how do we actually work across all of those disciplines, since they are all part of and needed for quantum information science. And most of our universities are not set up to work across all of those things. And that's actually a real challenge for the field right now that we're wrestling with, is how to pull those things together, how to work across those disciplines to actually make progress. But for the younger students, it's really about, none of this is in the classes. This is all new. And we tend to not teach it until the end of the university or into graduate school. That's usually when you first see quantum mechanics. You certainly don't see it in elementary school. And so what does that mean to get it at those ages?
Right, and that is also true in the humanities. There is no quantum mechanics that is discussed. But do you think that actually this is a very particular field? I mean, you probably know, and you can remind me, when physics became something related to ethics and to the humanities, which was the nuclear revolution, I think, right?
Well, I mean, physics has been around for a long time.
Yeah, but that is there's impacting society in a certain way.
Yeah, so I think certainly with nuclear technology and the development of the bomb, of course, that was a huge revolution in what is the role of a scientist in thinking about the ethics of what they create. I think that may be, and I'd have to go back, there may be a longer history of it as well, but I think that was certainly a moment where scientists had to rethink their role in a way that they hadn't before, because all of a sudden they were working on understanding the atom, understanding quantum mechanics, basically, and the implications were profound, right, and dangerous, and made a huge impact on our world in a way that wasn't necessarily positive. And, scientists have very different reactions to what that meant and what their role is and how to actually manage that. And we haven't always confronted it as directly, right? It's not necessarily as much a part of the education system as it probably needs to be, because each of these revolutions bring some implications that we didn't intend.
Wonder what is your take on the ethics of quantum?
Yeah, I mean, I think it's something we have to think about. And as an educator, I think it's something that we have to make sure the next generation is thinking about as they develop technologies, whether it's quantum or anything else. And I think I take AI as a bit of a lesson in all of this, right? It has gotten out ahead of a lot of thought around how do we govern it, how do we regulate it, and because of it, we have all sorts of challenges that have developed as AI has expanded extremely rapidly without any of those controls in place. And so I think it's incumbent on anyone working in science to be aware of the possible ethical implications of what they do, which isn't to say we necessarily don't move it forward, because the reality is it's going to go forward from someone somewhere, but we need to think about before it's out there, before it's too late, right? What are the implications? What are the implications of building a computer that can break our encryption? How do we manage all of that? I don't think the answer is to, well, we stop working on quantum computing because someone else is going to work on quantum computing. We're going to get there, but we need to actually be planning and working around it and having people think about how we deal with that ahead of time. And not, there tends to be, I think, in the scientific community, a wait and see approach. Like, well, we're not there yet, so we don't have to deal with it yet. And I think that's a little bit problematic. Because as we've seen with AI, if you wait, you may not have a chance. You can't put the genie back in the bottle. It gets too late. You have these problems with who has control, who has power over it, how much or lack of regulation has allowed things to happen that cause problems.
Yeah, but in particular, because AI has been explored quite a bit so far now. I mean, it's not ended the question,
No.
but in the quantum world, what do you think are these ethical risks, beside also the encryption?
Sure. I mean, and I think you alluded to sort of this question of power and control. I think that's always one. I mean, with encryption, there's privacy questions. And this is actually one of the classes I teach, I pose this to the students. Well, think about it beyond just sort of let's see if we can dig into this. One of the things that always comes up is, well, what are the energy requirements, right? This has come up with AI, so it's a thing that they look at fairly quickly as they try to think about it. Who has control of it? If this is going to produce new drugs, new things, right? Who gets access to those, and how do we make them accessible? Who has control over the software? Is it going to be the financial companies that actually want this technology to look at markets so that you won't have access to it to do some of the drug research, which could have positive implications for more people? How do we actually govern that? So starting to think, it's complex, and I'm sure these are only, sort of the surface questions, but it's not until we start digging into those and trying to ask them that we're going to know what the scope is, right?
Yeah, I mean, there is a question of equality after all, because whoever comes first with a quantum computer or a quantum algorithm that can solve big problems in medicine or elsewhere in the financial world, but also in the military world, then that is the famous kind of quantum supremacy. In a way, because they have more power, and they will use their power for their own interest. That could be a government, that could be a company, and there is no way to say to a government or a company that they should make that available to everyone.
Right. And so how do we think about who gets access and how that does? And I mean, I think government does have a role in that if they're willing to take it, to think about how that gets shared, how we share those resources. I mean, there's always push to use it for certain things, right? And how do we decide which ones? Especially because it will be expensive technology, right? It's going to take significant funding to make it happen. So how do we make it accessible?
This quantum revolution is even more affecting society than the nuclear revolution in a way, because at that time the scientists, the physics had to deal with the military mostly. I mean, that particular science was used in the military mostly. With quantum, it's not just the military including, but there is all the computing part, all the other society part, right?
Yeah, I mean, it's different, right? I mean, nuclear totally reshaped our world politically because of the military implications. So it's hard to say whether that's more or less, but it's certainly different now because there will be implications, whether it be through finance or through some of these other things that we've talked about, because others will have access to this technology or might have access and could actually have an impact on what happens based on how they use and manage that.